there is a place where our understanding of the universe unravels. It is a domain where the two great pillars of modern physics, the twin triumphs of the human mind, clash in a violent paradox. This cosmic fault line runs through the heart of a black hole. It defines the very first flicker of existence, the moment of creation. Here, in these crucibles of extremity, our science fails us. For a century, we have lived with a profound schism in our comprehension of reality. On one side stands a towering monument, Albert Einstein's theory of general relativity. This is a majestic description of the large-scale cosmos, a symphony of planets, stars, and galaxies. It reveals a universe where space and time are not a static stage, but a dynamic, malleable fabric. Massive objects warp this cosmic textile, creating valleys and curves we experience as gravity. General relativity paints a picture of graceful, continuous elegance. The Earth orbits the Sun not because of a mysterious pull, but because it follows a straight line through a region of spacetime curved by our star's immense presence. This conception of the grand totality has been verified with breathtaking precision. From the bending of starlight to the rippling of gravitational waves, Einstein's vision endures. Then there is the other side of this conceptual divide, the quantum world. This is a frantic, electrifying description of the universe at its most minute. It governs the realm of particles, atoms, and the fundamental forces that bind them. Here, certainty dissolves into a haze of probability, and energy arrives in discrete packets or quanta. The smooth, predictable dance of celestial bodies gives way to a jittery, unpredictable chaos. Quantum mechanics tells us that at its foundation, existence is pixelated. An electron can be in multiple places at once until the moment it is observed. Empty space itself seethes with a broth of virtual particles popping in and out of being. This bizarre and counterintuitive model is the most successful scientific framework ever devised, enabling everything from lasers to the computer chips that power our modern civilization. For decades, these two narratives have coexisted peacefully, each reigning supreme in its own domain. Relativity choreographs the cosmic ballet of the immense. Quantum theory orchestrates the frenetic rave of the infinitesimal. The trouble begins when their jurisdictions overlap in places where the immensely massive is also incomprehensibly small, forcing a confrontation between these two rival monarchs. Imagine the heart of a collapsed star, a black hole's singularity. General relativity predicts a point of infinite density where the fabric of spacetime is torn asunder. The equations break, yielding nonsense, a clear signal that the theory has reached its limit. Quantum physics insists that on such a small scale, uncertainty must reign and infinities are forbidden. One system demands a smooth, perfect point. The other requires a fuzzy, energetic blur. The same impossible contradiction appears at the dawn of time. Our understanding of the Big Bang traces the expanding cosmos back to an initial singularity. This was a moment when the entire observable universe was compressed into a space smaller than an atom. To truly grasp that primordial state, we need a theory that can handle both extreme gravity and quantum phenomena. We require a unification, a single coherent story that can be told about reality. This quest for a final theory, a so-called theory of everything, became Einstein's final obsession. He spent his later years searching for a master equation to unite his theory of gravity with the other known forces of nature, but the puzzle eluded him. In the years since, the search has consumed the lives of the world's most brilliant minds. It has been called the greatest unsolved problem in all of science. Grand and ambitious frameworks have been proposed along the way. String theory, for one, imagines that fundamental particles are not points but microscopic vibrating filaments of energy in higher dimension. Different vibrations of these strings give rise to all the particles and forces we see, including gravity. It is a proposal of breathtaking mathematical beauty and scope. Another leading contender, loop quantum gravity, takes a different approach. It suggests that space-time itself is not continuous but woven from discrete quantized loops. These elemental threads form a spin network, a cosmic tapestry of interconnected nodes. From this perspective, space is not empty. It is a structure, and time flows in indivisible ticks. This idea boldly attempts to build the universe from the ground up. Both of these avenues of thought have provided profound insights and powerful tools. Yet, after decades of intense research, neither has produced a complete or verifiable picture. They have become vast, intricate cathedrals of mathematics, beautiful to behold, but with no definitive bridge connecting them to the world we can actually measure. The grand schism has remained a chasm at the very heart of physics. But now something new is stirring in the landscape of theoretical science. A different idea, coalescing from the insights of its predecessors, has begun to emerge. This nascent framework does not begin with vibrating strings or quantized loops of space. It starts with an even more elemental and radical concept, the notion that reality is not built of things at all. The foundation of existence, it suggests, is constructed from pure relationships. This emerging vision, a synthesis we might call causal geometric unity, proposes a startling thesis. It argues that the most fundamental aspect of the cosmos is the principle of cause and effect. Before space, before time, before matter, there was a simple logical chain. This event caused that event. The universe, in its most basic form, is an ever-expanding network of these causal links. Everything we see and experience is an emergent property of this immense primordial information network. Consider the very concepts of space and time as we know them. In this new picture, time is not a river that flows, nor a dimension to travel through. Time is the irreversible unfolding of the causal web, the ticking of one event giving rise to the next. It is the universe's fundamental process of computation, the step-by-step processing of information. The arrow of time is built into the very logic of the cosmos from the beginning. And what of space, the vast emptiness between the stars? The framework of causal geometric unity sees space as a measure of connectivity. It is a reflection of how many causal links separate any two events in the grand network. Things that are close are separated by few links. Distant galaxies are separated by trillions upon trillions. Space is not a container for the universe. The network itself times the spatial geometry. This changes everything we thought we knew about the fabric of reality. Gravity is no longer the curvature of a pre-existing space-time stage. Instead, the force of attraction is a direct consequence of the network's intricate geometry. A star or a planet is a region of immense energy, a hub of incredibly dense causal connections. This density of connections alters the pathways through the network, creating what we perceive as a gravity well. An object moving through the cosmos is simply following the path of least resistance along the relational fibers of this universal structure. Its trajectory is not dictated by a force pulling on it, but by the very shape of the underlying grid. The awe-inspiring beauty of general relativity emerges naturally, not as a fundamental law, but as the large-scale statistical behavior of this unimaginably complex causal web. And what of the quantum world with all its maddening uncertainty? This new conception suggests that the network has a fundamental discreteness. There is a smallest possible unit of causation, an atom of space-time. These are the pixels of reality, the irreducible events from which all complexity is built. The jittery probabilistic nature of quantum mechanics is a reflection of what happens at this deepest level. When we are not looking, a particle exists as a wave of potential pathways through the network. The act of measurement forces a specific set of causal links to become definite. Uncertainty is not a sign of our ignorance, but a foundational property of the network itself. At its finest grain, the cosmos is a thing of pure potential, a shimmering sea of possibilities that crystallizes into concrete reality event by event, moment by moment. Suddenly, the great schism between the two pillars of physics begins to dissolve. The smooth, curving universe of Einstein is the macroscopic view of the network, like seeing a high-resolution photograph and perceiving a continuous image. The pixelated probabilistic world of quantum theory is the microscopic view, like zooming in until you can see the individual dots of ink that make up the picture. There is no longer a contradiction, only a difference in scale. One set of laws describes the behavior of the network in bulk. The other set of rules governs the interactions of its most fundamental individual nodes. This powerful synthesis offers a path to finally address the mysteries that have haunted us for so long, the places where our science has historically broken down. Let us return to the heart of a black hole. Causal geometric unity completely reframes the problem of the singularity. Because the cosmic network is built from discrete fundamental units, there can be no infinite compression. The fabric of reality has a finite resolution. It cannot be torn. A collapsing star can only squeeze matter and energy down to the ultimate density of the network itself. The center of a black hole is not a point of nothingness, but something far more extraordinary. It represents the most densely connected, most computationally complex region in the entire cosmos. It is a state of ultimate matter, where space and time as we know them lose their familiar meaning, but where the underlying causal logic remains perfectly intact. Information is not destroyed, it is simply woven into this hyper-dense sector of the universal tapestry. This perspective may even solve the famous black hole information paradox. What falls into a black hole isn't lost forever. Its causal connections to the outside universe remain encoded in the subtlest of ways, perhaps through the faint whisper of Hawking radiation, which now can be seen as the slow leakage of information from the network's most compacted zone. The same powerful logic can be applied to the very beginning of everything. The Big Bang was not an explosion from an infinitely dense point into a pre-existing void. Such a concept has always been a placeholder for our ignorance. This new paradigm offers a more coherent and elegant origin story. The universe may have begun from an incredibly simple state, perhaps a single causal event. This primordial atom of becoming contained within it the potential for all that was to follow. The Big Bang was the moment this initial node began to branch, to expand, to create new connections. It was the start of the great causal chain reaction that is still unfolding today, 13.8 billion years later. The rapid expansion of the early cosmos was the explosive growth of the network itself. It created space and time as it grew, weaving the very fabric of existence from pure logic. There was no before the Big Bang, because the concept of time requires the sequence of causal events. The first event was the beginning of the clock, the genesis of before and after. The question of what caused the first cause may be the final mystery, perhaps pointing to a deeper substrate of reality we cannot yet imagine. Or perhaps it is simply the ultimate brute fact that from nothing a logical process began. This emerging theory does more than just solve old problems. It presents us with a radical new identity for the universe and for ourselves. If reality is fundamentally a network of information, then the cosmos can be seen as a colossal evolving computation. Its laws are not imposed from outside, but are the inherent rules of the network's operation. The complexity we see around us, the formation of stars, the evolution of life, the emergence of consciousness, is the result of this cosmic process exploring its own potential. We are not mere observers of this universal unfolding. We are a part of it, a complex and self-aware pattern that has arisen within the causal web. Our thoughts, our choices, our very existence are an expression of the cosmos becoming aware of itself. This is a profound and perhaps unsettling realization. It blurs the line between physics and information, between matter and mathematics. The stuff of the world is not solid, tangible substance in the way we intuitively feel. The elemental reality is the abstract logical relationship between events. Everything else is an emergent phenomenon, a shadow play projected by this deeper process. But is this just another beautiful mathematical idea destined to remain an elegant speculation? Or can causal geometric unity make predictions that we can actually test? The answer, excitingly, seems to be yes. If spacetime is made of discrete fundamental units, this pixelation might leave a subtle imprint on the cosmos. It could be a signature that we are on the verge of being able to detect. For instance, light from the most distant cosmic explosions travels for billions of years to reach us. If it is traveling through a discrete, granular spacetime, high-energy photons might be affected differently than their lower-energy counterparts. They might arrive at our telescopes a fraction of a second later than predicted by conventional physics. Our next generation of gamma-ray observatories are being designed with the sensitivity to look for this tiny discrepancy. Another place to search for clues is in the faint afterglow of the Big Bang itself. The cosmic microwave background radiation is a snapshot of the universe when it was just 3,800,000 years old. The patterns of temperature fluctuations in this ancient light hold a treasure trove of information. A theory of quantum gravity would predict a unique set of primordial fluctuations, a specific statistical signature that could be hiding in the data we are painstakingly collecting. And perhaps the most direct evidence could come from gravitational waves. These ripples in the cosmic fabric, first detected in 2015, have opened a new window onto the universe. They allow us to observe the most violent events, like the collision of two black holes. If these cataclysms are playing out on a discrete causal network, the resulting gravitational waves might carry subtle echoes or distortions that betray the underlying granular structure of spacetime. The search is on. Across the globe, physicists and astronomers are developing experiments and analyzing data, pushing the boundaries of what we can measure, hunting for these faint whispers from a deeper reality. This is no longer a matter of pure philosophy or abstract mathematics. The question of the ultimate nature of space and time has entered the realm of experimental science. What is at stake is nothing less than a complete revolution in our view of the world. Ever since the dawn of science, we have sought to understand the universe by breaking it down into its smallest constituent parts, atoms, particles, forces. We assumed that if we could find the ultimate building blocks, we would understand the whole. This new perspective turns that entire approach on its head. It suggests that the ultimate reality is not the blocks, but the connections between them. It is the architecture, not the material, that is fundamental. The universe is not a collection of things. It is a single, integrated, evolving story, a narrative of cause and effect, where every event from the tiniest quantum leap to the merger of galaxies is a sentence in a cosmic epic that is writing itself into being. We stand at a remarkable moment in the history of human thought. The greatest mystery of the past century, the gaping chasm between our two best descriptions of reality, may finally be closing. The answer, it seems, was not to be found in one theory or the other, but in a deeper principle from which both of them spring. The solution was to abandon our most cherished intuitions about space, time, and matter. The journey has led us to a strange and beautiful destination. A universe woven from logic where geometry emerges from information. A cosmos where time is the measure of change and space is the measure of relation. A reality that is fundamentally discrete, dynamic, and computational. It is a vision that is both profoundly abstract and intimately connected to our own existence. The final chapter in the quest for a theory of everything is not yet written. This emerging synthesis will be challenged, tested, and refined in the years and decades to come. It may be that this path too leads to an unforeseen dead end, but for the first time we have a framework that seems to possess the power to speak the language of both the quantum and the cosmos, a grammar for all of reality. We look up at the night sky, at the silent, majestic sweep of the galaxies, and we look inward at the frenetic quantum buzz from which our bodies are made. We see two different universes, one vast and smooth, the other tiny and chaotic. Yet we are now beginning to glimpse the underlying code, the hidden operating system that connects them both and that connects us to it all. The long search for unification has taught us a final, humbling lesson. The ultimate truth of existence may not be something we discover out there. It may be a principle so fundamental that it is imprinted in the very structure of reason itself. The great cosmic code is not a mystery to be solved, but a language to be learned, and we are at last just starting to become fluent.